In this tutorial, we're going to simulate a very simple RF circuit consisting of a transmission line with a load at the end of it. We will be looking at the effects that different loads and different lengths of transmission line have on the reflection coefficient and input impedance seen by our generator. The first thing that we need to do is go to Project Options and set the frequency of operation that we want to work at. In this case, it'll be 1 GHz. So we type 1 in this box, select a single point, and then apply. Now that we've selected the frequency of operation, we may also want to change our global units. So we go to the Global Unit tab, and we want to select units for inductance and capacitance that make it relatively easy for us to work at the frequency of 1 GHz. The inductance is fine, nanohenries should do the trick for our circuits at the frequency of interest, but for capacitors we choose something a bit smaller. We'll choose picofarads. And then click OK. Now we open a new circuit schematic by right-clicking, selecting New Schematic, and giving it a name. We'll call it TX line load. The first element that we need is a measurement port, and you can find it right up here. You click to place it on the schematic. So we have seen how a port basically represents a signal generator of the frequency that we set in the project options with an internal impedance equals to Z, which in this case is 50 ohms. The other thing that the port is able to do is to measure directional power. So it can actually measure what power goes out of it and what power is reflected back into it. And this is of course very important for the measurement of the reflection coefficient and in turn of the impedance. Now we'll start with a very simple load. We'll start with a simple resistive load which is equal to 50 ohm. We press Ctrl L to pull up a new element. We type RES and then we select the res element, which is a simple resistor. Right click to turn it the way we want it, place it on the schematic, and then put a ground connection at one end of it. Now we must set its value to 50 ohms. We still need to connect our port, so our generator, to the load, and we will do that through a transmission line. There are several types of transmission lines that we could use, and I will be going through all of them in the future, but for now I will just use a transmission line whose length is specified as electrical length. So again we press Ctrl L and we type T-lin and select the T-lin element from the list. Place it on the schematic and then connect it to the port and to the load. Now let us look at this element a little bit more closely. We've got the characteristic impedance of the line, Z0, and that is 50 ohms. As we said, we want that impedance to be the same as the internal impedance of our signal generator, which in this case is our port, so 50 ohms. The electrical length is set to 90 degrees. We'll just give it a random value, say 20 degrees. And then F0 is the frequency at which the electrical length is calculated. Don't forget that the electrical length is equal to beta L, where L is the physical length of the line and beta is 2 pi over lambda. We know that lambda of course is related to frequency, so we need to have a specific frequency to specify an electrical length. So remember that the electrical length of a line is always specified in relation to a specific frequency. For this element, the frequency with respect to which the electrical length is defined is F0. So we'll need to change this to 1 GHz, which is 1000 MHz. So we've got our circuit set up. You can see that the internal impedance of the generator is 50 ohm. The characteristic impedance of the transmission line is also 50 ohms, and that our load is also 50 ohm. So we've got RS equals Z0 equals RL. And we know that this means that we'll have maximum power transferred to the load and no power should be reflected. So let us set up a measurement that allows us to verify just that. We can go to Graphs, right-click, select New Graph, and then Polar Plot. Let's call it Gamma. Now, remember that in Microwave Office you won't find a gamma measurement specified. You will have to use an S11 measurement. We've looked at this and we've seen how S11 and gamma, so the reflection coefficient and the S11 parameter, are the same for a one-port network. That is because gamma does nothing but measuring the ratio of the reflected power over the incident power. And remember that S11 looks at the ratio of the power reflected into port 1 over the power that was outputted by port 1. So this is exactly the same thing. So we now right-click on the graph, choose Add New Measurement, and then we need to choose linear, port parameters, S parameters, to port 1 from port 1, because we want to see the power that gets reflected into port 1 when the signal originated from port 1 itself. We'll also select the schematic from which this measurement comes from, STX line underscore load. Click on Apply and then OK. Now let's simulate. We can see that the value of the reflection coefficient is bang on in the middle of the polar plot. So it is 0, because obviously in the polar plot we would plot our reflection coefficient in terms of its magnitude, which is the distance from the center of the plot, and in terms of angle, which will give us its position, its radial position along the polar plot. Now notice one thing. Microwave Office often auto-scales the graph. So if we now look at the top left-hand side, we can see that the radius of the plot is 1.2 times 10 to the minus 10. So it's very, very tiny. So there are two things that we may want to do to make sure that we know what we're looking at. First of all, we can right-click on the graph, go to Properties, and then Grid, and take off the auto limit and say that we want a minimum of 0 and a maximum of 1. So we end up with a unity radius circle. Click on Apply and OK. Now you can see how on the top left hand corner the maximum magnitude has become 1, which tells you that the radius of your of the outer circle of the polar plot is actually 1. The other thing that we may want to do, because some of you will want to copy and paste these plots somewhere else, and they may need to modify the fonts, is indeed modify the fonts of whatever is written on the graph. For example, we like this bit here and this bit there, for instance, to be a little bit bigger to make them more legible. This is easily done. Let's just right click here, go on to Properties again, and then on the Fonts tab. We can then go on to Labels, and we can select a bigger font for our label, say 24. Click on OK, and then Apply. And now you can see that these values are shown in a much more prominent way, maybe even a little bit too prominent. So the first thing we'll do now is go back to our schematic, TX line, and we will use the Tune tool to change the length of the transmission line and see in real time what effect this has on the reflection coefficient, gamma, or equivalently the S11 port parameter. So I just click on the Tune tool and then click on the quantity that I want to tune, the electrical length in this case, and press Escape. We'll go back to the graph and then we'll open the tuner, which is this slider up here. You can see that the electrical length now is right there. And we'll tune it between 0 and 180 degrees. That's because this way we'll be able to sweep the whole polar plot. Well, you can see that as I change the length of the transmission line, nothing is changing at all. And this is because, although the reflection coefficient is changing in phase, so it's actually rotating around, its radius is 0. It is basically rotating around a circle of 0 radius, and hence you don't see move at all. So, now let's go back to our schematic and change the load this time. So we will change the load to a resistance which is less than the characteristic impedance of the transmission line. So Z note is 50 ohms, and we'll go for a 25 ohm resistor instead. First of all, we'd like to see what happens when we have a very, very small line between our generator and our load, so between the port and the load. We can do that in two ways. We can either simply connect the load to the port, or we can just set a transmission line length to 0 degrees. Let's close the tuner for now. So we set the transmission line to 0 degrees, which means that effectively there is no line between the generator and the load. As I said, in simulation we could have simply connected the port to the load with the usual wiring tool. However, we'll just keep the line in, because we'll then want to see what happens when you change the effective length of the line. And also it is important to have a practical idea about how these things are done in real life. And of course, when you are using a measurement setup and you have a port on there which you want to connect to your load, usually you will have some sort of length of line, which sometimes may be ignored, but a lot of the time you have to take into account. So let's simulate and then go back to our gamma plot. Now you can see that in this case gamma has a finite value, and Microwave Office has kept the scale that we had before, so the radius is still 1, and you can see that we are about a third of the unity radius away from the center in this case. But don't take my word for it. You can either just click on the marker that represents the point that we plotted to see the actual value, like so, or you can actually have a marker put onto it. This is very simply done, and there are two ways to do it. Either you right click and you select add marker, or, and this is a way I prefer to use, press Ctrl M and then click on the point of interest, and you get your marker. Now there are a couple of things here that we need to point out. First of all, the marker readout. You can see that at the moment, as a marker readout, we've got the real part and the imaginary part. So we're basically having a Cartesian form for the S parameter S11, or reflection coefficient gamma, whichever way you want to see it. But we may want to have that value in a different format. You know, it's a complex number and it can be displayed in different ways. The other thing that we may want to have, again, if we need to copy this plot somewhere else and we need this value to be very visible, is to change the font of the markers. So again, let's right click, go on to properties, and again to fonts, and go to markers, and then I want to make my marker a little bigger. Probably I won't go all out as I did earlier, so I'll choose 20, click OK, and apply. And now you can see the marker really clearly. The other thing that I can do is right click on the graph, go to properties and select the markers tab. Now here you have various options which are very useful. First of all, the display format. You can display the value which you read out as a real and imaginary part, so Cartesian form of the complex number, magnitude and angle, which is the polar form of the complex number, and magnitude and angle in dB if you want to have a logarithmic scale. So for example, I can just select magnitude and angle, click on apply, and you can see that immediately you are told that the radius of your reflection coefficient is 0.33 and the angle is 180 degrees, which is what it is indeed. Okay, so we've had a look at the reflection coefficient now, but we've also seen that there is a direct correspondence between reflection coefficient and impedance. And we can plot the impedance on a Smith chart. So, let's do just that. We right-click on Graphs, New Graph, and we choose Smith chart. So in this case, we call this impedance. And now we've got the Smith chart, as you've seen already. To make the chart more legible and not quite so dense with lines, we can right-click on it, click on Properties, and then on the Grid tab, we can select the contour density under contour lines. At the moment, we're just using the default, but we could also have a coarse contour density, which means we'll see less lines. And in some instances, this may be advisable. I will do it in this case. So I'll just click on Apply, and then OK. Now, as we did before, we must right-click on the graph, click on Add New Measurement, and again, we click the S11 there. Now, you may say, why aren't you picking the impedance? Well, there is a direct correspondence between S11, which is reflection coefficient, and the impedance. And also, as we've seen, the Smith chart is nothing but a polar plot of the reflection coefficient upon which we superimpose a mask. So if I plot the reflection coefficient on a Smith chart, I should get the right value plotted on there, and then I can read out the impedance from the Smith chart grid. This will become apparent in a second, bear with me. So click on Apply and OK. As you can see, there is no reason to resimulate because the value is already there. And if I click on it to see what it is, I get a value of 0.5 for the real part of the impedance and of 0 for the imaginary part, the reactance of the impedance. Again, what I can do is press Ctrl M and then click on the point of interest so that this value is displayed constantly. Then I can right-click on the graph, click on Properties, go to Markers. You've got the display format there, which you can pick to be whatever you want it to be. So for example, you could choose magnitude and angle and click on Apply, and then you would get these values. But also, you can denormalize the impedance to whatever impedance you've normalized to. At the moment we are in a 50 ohm system. We've chosen our port to have a 50 ohm impedance, so that effectively sets the whole impedance of the system. We just select denormalize to 50 ohms, click on Apply, and you can see that now you get 25 ohms right there. Now, we want to see what happens as we change the length of the transmission line. But before we do that, I just want to display a couple of things side to side. Let me just close the schematic by just selecting Window and Type Vertical. You can see that we've got the reflection coefficient on the right hand side and our impedance on the left hand side. But they're representing exactly the same point. The only difference is that one is a polar plot and the other one is still the polar plot, but upon that polar plot I've put a mask so that I can read out the impedance easily. So I'm going to leave these as they are, and then I'm going to open the Tune tool so that I can change the electrical length of the transmission line yet again and see what effect it has on the graph. Now notice how the points move in unison between the two graphs. This is just to reiterate that what you're looking at is the reflection coefficient, but on the graph on the left hand side you can read out the impedance immediately, and that is actually the advantage of it. So look, if I go around the whole range that I've set for the electrical length of my transmission line, I go around a 360 degrees circle around the center of the Smith chart, or if you will, around the center of the polar plot. Now if I go back to 0, I'm back where I started. Notice how when you increase the electrical length of the line, you go around a circle centered around the center of the Smith chart, and you go around in a clockwise direction. And we have seen this in the book. This is just what happens. It comes out of the maths, but it is just the way it is. Remember, when you increase the length of the line, you're going around in a circle in a clockwise direction, just like so. Now, suppose that you want to see this a little bit more clearly. So you don't want to have to use the tune tool to see what circle is described by the changes in length of your transmission line. We can do that very easily in MicroOffice. Let's close the tune tool, go back to our schematic, and then take away the tuning from the electrical length of our transmission line. Now we'll insert a variable here, and we call it EL underscore range, and we'll give it a value of 0. This value is completely immaterial. I am just defining a variable which I will then sweep, and I have to, because of the way the simulator works, declare this variable separately and give it an initial value. Then I can connect it to the sweep element, which we'll get in a moment. So now if we press Ctrl L and type in VAR, you can see that you get an element called swept variable. We place that on the schematic. Now, first of all, we need to set the variable name, and that is EL underscore range. We've just defined that. Now, in terms of the values, we can change them in two ways. We can either type them directly in here as a list of values, or we can just right-click on the element, go to Properties, and then when it comes to values, we define a range as a minimum, a maximum, and a step between the two. So we can have a full range defined automatically. And this is done by typing stepped initial value, which is 0, final value, which is 180, and let's say that our step is 10. So now our variable EL range will have values between 0 and 180 in increments of 10. Now the last thing that's left to do is to assign the variable EL range to the EL parameter of our transmission line element. So instead of any number here, we just type EL underscore range, and we are done. Let's go back to our graphs now, and let's take a look at our measurements. Go to Modify Measurement, and it tells us what do we want to do with the swept variable, and we select here Plot All Traces, because we want to see all the values that the reflection coefficient or the impedance assume for every different values of the transmission line length in the range that we've set in our swept variable. So let's put these two graphs side to side as we did before, and then click on Simulate. Let's move the markers out of the way a little bit. Or we can just delete them if you like. And you can see how both on the polar plot and on the Smith chart we get a circle which is described by the transmission line length increasing. And the circle, as we've seen with the tune tool, is described in a clockwise direction as the electrical length of the line increases.